Okay, this is going to be the first in a series of videos that wraps up topic 11/21. The topic is on measurement and data processing as well as analysis, so analytical chemistry. As we're going to look at it right now, it's going to tie in very closely with the organic chemistry unit, and we're going to be looking at some different analytical techniques that get used to analyze what a molecular structure actually is. So we always talk about how we've got ethanol or we've got pentane or something like that, and we have these chemical formulas and we can draw their structural formulas, but how do chemists actually have a chemical inside of a test tube and figure out what its molecular structure truly is, beyond just being told it on the bottle or on the label. So that's what we're going to look at here. What are the different devices and what are the different readouts, graphs, and things that we're going to get that allow us to figure out what the structure is. Identifying a structure is very complicated, and it usually involves a lot of different pieces of data being put together. And when you combine them all, you can get a picture of what the compound actually looks like. Just one of these techniques on its own is usually not quite enough to figure out with certainty what a structure might be. So one important piece of information for determining a structure is knowing its percent composition or its empirical formula. This is something that we've talked about in earlier topics, but it's going to come back and we'll review it while we do topic 11 and 21. There's also going to be the mass spectrometer, infrared spectroscopy, proton nuclear magnetic resonance, or HNMR, both low and high resolution for the HL class. And we're going to look very briefly at a technique called X-ray crystallography. This video, however, is focused on the mass spectrometer or mass spectroscopy. So in a mass spectrometer, you insert a sample. That sample is vaporized, so it's in the gas phase, and then it's ionized with an electron gun. So something that actually fires lots and lots of electrons at the substance, and that gives the substances positive charges. The little particles end up with positive charges because the electrons end up knocking off other electrons when they collide. Once the things have turned into ions, now they can be accelerated. They're made to move really quickly through this chamber. And then there's a giant electromagnet which pushes on them perpendicular to their motion and causes them to, as they're moving through it, deflect or curve off in this direction. Now, if the particles are really heavy, then they won't be affected much by that electromagnetic and they might crash into the walls. If the particles are really light, they might swing off and crash into this wall. But the electromagnetic magnet can be adjusted until the particles are deflected just right, that they end up making it down this next chamber and hitting a detector screen. So based on where exactly they hit on the detector screen, both their mass and their charge, or at least a mass to charge ratio, can be determined. You don't have to be able to explain the operation of the mass spec, but I thought it might be helpful to show you. The ionization process can be essentially thought of as, here's a gaseous atom. I'm going to knock on it with an electron, and as a result, I'm going to turn it into a positive ion. And now there are two loose electrons. One of these electrons is the original electron, and one of the electrons is one that got knocked off of the atom. So it looks similar to ionization energy, but we're showing the additional electron that's coming from the electron gun. There actually are lots of different positive charges that can be formed in this ionization process. You can form 2+ and 3+ ions as well. But the machine can be adjusted until the 1+ ions are the ones that are being detected. And that works because the higher the charge, the more the ions get deflected. So the 1+ ions are the ones that get detected when the magnetic field is at a fairly high strength. So essentially, you could trust that only the 1+ ions are the ones being detected. And the machine actually measures a mass to charge ratio, M to Z ratio. But if the charge is 1, if we plug in 1 for the charge, then the mass to charge ratio really just gives us a mass, or a relative atomic mass, a relative molecular mass. So we've seen mass spec readouts before when we did isotopes way back in atomic structure. And we used it to get percent abundance and to get the masses of different isotopes. And from that, we could average it out. But notice it does give us mass to charge ratio, but you could just treat these as the actual masses of the different isotopes. What's going to be different when we look at this for molecules is, one, we're not really going to care about the abundance as much, how high the peaks are. We're really only going to care where they are, what the masses are of the different peaks. And the reason for that is that if we send molecules through a mass spectrometer, like organic molecules made of carbon, hydrogen, oxygen, through this mass spec, the electron gun not only creates positive ions, it actually can break some of the covalent bonds, which results in the molecules actually splitting and breaking apart into a variety of little pieces or fragments. So when you get a mass spec readout for a substance that's a molecule, instead of just a single atom like the isotope readouts, what you actually are looking at is like a fragmentation pattern. So you've taken these molecules and you've basically shattered them apart, and they've created all these little pieces of these molecules. And the machine can detect how heavy the different pieces are. The peak that you'll see in the readout that has the highest mass, but again, not the abundance. We don't really care about the abundance. The peak for the highest mass, or with the highest mass, is called the parent ion. And that represents basically the original molecule with just one electron lost. And so the heaviest peak that you see in there is basically the molar mass of the substance, the molecular mass of the substance, where all it's lost is one electron. So it still has the mass of the original molecule. And then you can sort of predict what other peaks might show up in the spectrum based on the structure. So let's use ethanol and its likely fragments, I should say, likely fragments, plural. Okay, so first off, the parent ion of ethanol would just be ethanol with a positive charge somewhere on it. So one of these atoms has lost an electron, so this is the parent ion. So it would have a molar mass or molecular mass of about 46. So we would expect that on the mass spectrum of ethanol, there is some sort of peak at the M to Z value mass to charge ratio of 46. But there are also these other ones that we can predict. So let's think. Here's one bond that we could break. We could break off a hydrogen. Now, there's so many places I could break off a hydrogen here. I'm just going to pick one. I could obviously break that hydrogen off or this hydrogen off. But if I think about what's a covalent bond that is possible to break, just want to do this cleaner, I could definitely break a hydrogen free. And so if I think about what those two fragments are, if I form H+, then I'm going to have a fragment that weighs 1. And if I have this one with a positive charge so that it gets detected, I would have a fragment that weighs 45. So when we look at the mass spec, we may end up seeing a peak at 1 or a peak at 45. I'm going to give you a little heads up that we don't ever really see the peak at 1. The hydrogen ion, or hydrogen rarely forms the plus ion in these scenarios. So we're probably going to see a peak at 45, but we may not see the other half of that one at 1. Another place where this molecule might break is right here. This covalent bond. Oh, I skipped one. Sorry. We'll walk down the covalent bonds, essentially. Walk down the line and think about what the masses would be. So what if this bond breaks? Well, carbon plus 3 hydrogens, if that one turns into a positive ion, I would have a peak that weighs 15. And so this one, the remainder, weighs 31. So identifying the parent ion and the molar mass associated with it is really important, because then it allows me to quickly figure out what the two different fragments would weigh as I go down the line, as I go down the compound. So I may see a peak at 15, I may see one at 31. And sort of the last place to break is right here. And in this one, I have 15 plus this piece weighs 14, so I have 29. And that leaves 17 for the OH. Okay, so what I'm saying ahead of time is going in, I would expect to see a peak at 46, definitely, and then I would likely see all of these peaks, a peak at 45, 15, 31, 29, and 17, based on its structure and how it's possible for it to break apart. And so remember, this fragmentation pattern, this mass spec, is just one piece of data that we would use along with empirical formulas and molecular formulas to try to figure out the structure. Notice that a couple just little notes. In a real mass spectrum, there's often many, many, many tiny little peaks, and only some of them can be identified with certainty, because some fragments can further fragment and further break down before they hit the detector. So in your questions, it's very likely that you're going to get rather simplified spectra to only show the major predictable peaks. Okay. Also, the abundances aren't really of that concern, because the abundance sort of gives you a sense of how stable are the different fragments, and more stable fragments are going to be more likely to form, and so those peaks are going to be taller. But that's not really what we care about. What we care about are what are the fragments, not how abundant they are. So if we now look at the spectrum for ethanol, let's see. Here's 40, so this is 46. So there's definitely a peak at 46, and the highest peak is at 46, and that matches up with the molar mass of ethanol. There's then definitely a very strong peak at 45, which we predicted. There's not a peak at 1, it's not even shown. So you don't always get both sides of the fragments when they split. Okay, but I do get a peak at 45, and that suggests that sometimes just a hydrogen gets knocked off and the rest of it weighs 45. If I look at the other major peaks, there's definitely a huge peak at 31, which was one of the ones we predicted. And we predicted that if there's one at 31, then there should also be one at 15 to add up to 46. Well, there is a peak at 15. It's kind of small. It suggests that it's not very common to form this one, but it is there. And so again, it's helpful to know the parent ion mass, because then you can look for the fragments that add up to that mass. The other one that we predicted was 29, and there's a pretty sizable peak at 29 right here. If I look for the corresponding one at 17, though, there's really barely anything at 17. So even though I expected there to be one at 17, it doesn't show up. And that happens sometimes. Sometimes there are fragments you expect to see that don't show up, and that just suggests that they're so unstable as a positive ion that they don't show up. And so the OH in this case hasn't really shown up much, except this tiny little blip. Okay? And these are the various peaks that match to the fragments that we identified on the previous page. So just to show you, in the data booklet, you are given a little bit of help, some very common fragments that show up in organic compounds, things like methyl groups, things like hydroxyls, things like ethyl groups or CHO groups from aldehydes, things like carboxylic acid groups. These all have sort of characteristic weights or masses, and they've actually done the hard work and added up the molar mass for you. So these are some common ones, and if you look at this table while you're doing a mass spec problem, it can help you identify what the different fragments might be. Okay, we're going to skip ahead a few pages, and we're going to check this one out. I think we're going to check this one out. Yep. Okay, so given, and this will be the last part of the video, and then we'll do the rest of the practice problems in class. So an unknown compound has an empirical formula of CH2O, and then you do the mass spec and you get the following spectrum. Okay, here's the data booklet table to help us. First step would be determine the molar mass of the compound. In order to determine the molar mass, I'm looking for what we call the parent ion, or the highest mass ion in here. And so I'm going to pick 60. Right, that's the big peak, and it's more or less the highest besides that tiny little thing that I'm not even going to worry about. So if 60 is the molar mass, right, then that's really useful, because if I have empirical formula and I have molar mass, right, so if molar mass equals 60 grams per mole, well, now I can compare that to the empirical formula mass. And the empirical formula was CH2O, and if I add that up, that weighs 30 grams per mole. And so that means that the actual molecular formula must be 2 times as big as the empirical formula. So the actual molecular formula, written down here, must be C2H4O2. So it's twice as big. So just from knowing the parent ion and the empirical formula, I can figure out the molecular formula. Okay? And this has a total molar mass of 60. Now, if I look at the spectrum, I'm going to try to identify some sort of common peaks, or some major peaks that exist here. All right, so one of them appears to be at 1, 2, 3, 4, 5. So one of them appears to be at 45. Another one appears to be at 43, which means if the total thing weighs 60, that I should be looking for fragments at 15, to go along with the 45. So here's a 15. And I should be looking for 17, which, there's a little tiny blip, but not much of anything. The other ones are pretty small, so why don't we just go there? I have a pretty small compound anyways, C2H4O2, and let's see what we can figure out based on this. All right, so I've got 15 and 45 seems like a definite one. So let's check it out. A common thing that has a mass of 45 is COOH, and a common thing that has a mass of 15 is CH3. Let's see what happens if I put those together. If I put together CH3 and COOH, right, and you imagine it breaking right in between the CH3 and the COOH, that's what produces the 15 and the 45 fragment. Well, let's count it up. I have 2 carbons, 4 hydrogens, and 2 oxygens. So this formula matches my molecular formula and matches 2 of these major peaks. And then I guess we could think about, could it also have a peak at 17? So it gets easier to do if you actually draw out the structural formula of what you think you might have. So the first example, we were breaking this bond. If I try to think of the 43 fragment, I need to cut off 17. And if we look in this table, a common 17 is OH. So even though I didn't see the 17 peak, the fact that there was a 43 peak suggests that there is a 17 fragment that maybe is just not showing up. And so this fragment, if I add it up, does weigh 43. So it would seem that from this mass spec and this empirical formula, a very likely candidate for what this molecule is ethanoic acid. Now, it looks like that's probably it. We'd probably want to run some other tests, use some other techniques to double check and make sure that these bonds exist in there and that this structure can be further confirmed. But based on this mass spec, right, I figured out the molar mass. With the empirical formula, I got the molecular formula. And with these peaks and the IB data booklet, I was able to come up with some pretty good ideas for what the fragments were and figure out how they piece together. And I made sure it matched my molecular formula. And then I'm pretty confident that what I've got here is ethanoic acid. I've got this carboxyl group along with a methyl group. So we'll do more practice in class, but that's essentially what you do with the mass spec. You get asked to interpret these printouts, these readouts, and also to predict and draw the different fragments.